Well, thank you, everyone, for joining. So I want to start off with talking about how user interactions in social media tell us a great deal about the real world. By understanding the time-dependent discussions and context around social media and public web outlets, we can identify and even predict important real-world events and trends. So today I'm here to talk about Project Fortis and how we're using a variety of platforms across the Spark streaming ecosystem to identify humanitarian crises and health epidemics around the globe. So just to introduce myself, I'm Eric Schlegel. I'm a senior engineer for the Partner Catalyst team. And the Partner Catalyst team was started about 2.5 years back, and it was started shortly after Satya came on as CEO to help drive innovation, not only across Microsoft, but also across all of our partners and our clients. And how we do that is we embed ourselves amongst the local development community and identify emerging trends in technology and use those emerging trends and use emerging stacks to drive, to basically build innovative solutions for our partners. And we do it all in open source on GitHub. So the one project I wanted to share is one where we started partnering up with the United Nations, more specifically the Office of Humanitarian and Coordination of Affairs, about a little over a year ago. And they're tasked with delivering humanitarian aid or constructing humanitarian aid plans for the most vulnerable individuals in the world based on these crises that are occurring. And these crises can range from refugee displacement to famine or to hunger or terrorist attacks. So some of the challenges that we first wanted to address when we worked with the UN OCHA was we wanted to, one, pick a targeted scenario of where we could actually focus a solution on. So we decided that we wanted to build a solution specific towards the Libya refugee situation from the post-Gaddafi world. So some of those key challenges we wanted to address that when OCHA is constructing these humanitarian aid plans is that they're often manually composed. So the way it works is when a humanitarian disaster occurs, you have a field office in a particular region. They start collecting information around social media outlets, public web pages, through local conversations, local individuals, contacts they have on the ground, through journalists that are in these areas. So all this results in imprecise aid relief plans due to the manual nature of these plans and the data gathering process. For Libya specifically, that operations team was monitoring 150 Twitter profiles a day, about 110 public Facebook pages a day, 10 radio streaming broadcasts, television broadcasts, local news and blog sites. They were doing this manually, and they were collecting and tracking the information in Excel. And often at times, these areas are very inaccessible. We're talking about some of the most dangerous parts of the planet. We're talking about Aleppo, we're talking Mosul, we're talking Benghazi. So they don't have access to these areas. So they often have to work remotely. So in Libya specifically, they were working within Cairo, which is the closest place that they could actually get to Libya. So in order to construct these accurate plans, you have to understand what people are talking about on the ground. And due to the manual nature, the slow turnaround time is a huge challenge. And often at times, the turnaround time is quite crucial. Having a quick aid relief response can decide whether people live or die. And actually, timing is absolutely essential here. So the goal of Fortis was quite simple. Could we search for humanitarian-related keywords in geolocated social media outlet discussions and other short messages and against real-world features, like within a city or state, and identify trends in conflict? So we want to accelerate the timing of these construction plans, improve the data accuracy. And with machine learning and forecasting and trend detection, be able to provide deeper insights so so the aid workers can able to slice and dice and understand the interrelationships between topics that they're tracking, keywords detecting, and impacted gender, and age groups, and sentiment. And then there's many situations out there that require for the research and diligence team to get real-time analytics into the situation. The scope of Fortis then grew after that engagement, where we started working with the World Health Organization to help drive, to help accelerate and gain more insight into the spread of Zika virus and dengue virus. So we're collecting weather forecast data, looking at temperature level information, precipitation level information to predict and infer where mosquitoes are going. Converging that data set with social media and conversations around how people are talking about symptoms of Zika virus, so fever, rash, things like that, and then correlating that with sentiment data. You could then see over time of how the situation for Zika in terms of the intervention, whether it improved or degraded. So with those goals in mind, we built Fortis, which at its core is a data ingestion, analysis, and visualization pipeline, fully built off of Spark. So enough demo side. Now to get to the showcase of Fortis. There we go. So the way Fortis works is we're simplifying the process right now to easily deploy a Fortis site. So an admin or our partner would then deploy a Fortis site to their Azure subscription. It would run, and based on the type of site they want to deploy, whether it's humanitarian or health, we have a predefined set of topics and keywords that we're tracking. Within the admin console, a user would be able to further condition those keywords and topics, define what Facebook pages they want to monitor, what are any blacklist terms they want to filter out. So if you're monitoring, say, Benghazi, you want to filter out any references saying Trump or Hillary or Clinton. So having more control on that site. So when you first go to the site, you see what are the most popular terms, topics, sources, and locations from the pipeline that we're collecting. And everything is built off of, is very spatially context. So as you zoom in, you see all the conversations based on the topics that you're tracking. So in this case, we show the most popular topic here is attack. And the color in the cluster map here is indicative of the average sentiment that we're tracking. The number is the number of mentions, the aggregate count. So if you wanted to filter it further and say, show me all mentions of, say, attack and airstrikes. So here we have an event. If we open this event up, this is talking about the Manchester bombing in London. Oh, it's not showing up. Yeah, rendering's some issue with the rendering. It's showing up on my screen. Sorry, I'll just talk through it. So when you click on that, there is a modal window that pops up to show the actual detailed article that we're collecting from public web. So the data sources that we're collecting this information from is Twitter, Facebook, Instagram, radio streams, as well as public web through Bing. In terms of the Bing piece, oh, no. It's not switching over for some reason.
You're on one. It's seeing it. There it is.
Oh, OK. Sorry about that. OK. So as you zoom in, here we're looking at an event that we're filtering off of attack and off of airstrike. So as we click this event here, this is the detailed article that we're collecting from the public web. So you have a direct link to the original publication. And here it's talking, the reason why it's relevant to Fortis in Libya is because the bomber was trained in Tripoli. You are able to see a time series view on all the mentions over time and how that's changed. So this is where we're putting a lot of more effort for the version 2 of Fortis. We're able to do, we're building out a linear regression model in Spark using Spark ML to do trend detection and labeling trends off of this time series. Also being able to bring in sentiment and other demographics so you can see what those interrelationships between sentiment and, say, gender and an age group are. So the idea of Fortis is to not just deploy one site, but you can almost deploy hundreds, if not thousands of sites to validate certain scenarios of how specific targeted events and the sentiment and the public opinion around those events. And the visualizations here are fully elastic. So you can actually move these components around and then stretch them out. And the data queries here are all powered by GraphQL. So within the admin interface, you could actually go in and define your own GraphQL queries. When you first deploy a site, you get a default query that backs each visualization, but an admin control that understands GraphQL can easily change that. This whole cluster of Spark that we have stood up is running off of Azure Container Services and Kubernetes. So this is our cluster here. We're using Helm, which is the package manager for Kubernetes, which is pretty much a predefined package that you are able to, in a repeatable process, be able to stand up a given resource. So we have a Helm chart that we've contributed for Spark, and then one for Cassandra. And then the Helm chart here for Spark, within the values.yaml file, you can specify all the memory limitations and memory resources you want to allocate to your master node, as well as here. So here on the worker node, we have a number of replicas. So you can specify the number of worker nodes you want to deploy. And then the Bing piece, with Bing, you can then specify what type of sites do you want to start monitoring? What sites are more boosted than others? So you have a concept of you have a boosted site and a super boosted site. And then you could control the order of which one's more relevant than the other. And then the research results come back. And then you could actually train your search query to say whether or not that's relevant or not. And then they create a REST endpoint around that search instance. We take that, and then we create a Spark streaming connector around that to create that as a RDD coming through our pipeline. So the data pipeline comprises of, we make heavy use out of Spark streaming connector extensions. So we have one streaming connector for all the data sources we're collecting data from. And I'll go into this more in depth. The social and public data sources come through as a D stream, which is basically the abstract data structure around Spark streaming. So we're able to take all these D streams and unionize them together. Events are processed, transformed, and merged through Spark. We use Cassandra as our state engine for aggregation. And then the results of our transformation ETL process are written to Event Hub for the sole purpose so that GraphQL subscriptions can then actually respond and re-render those results onto the interface. So GraphQL just came out with this concept of subscriptions about a month ago. Which basically they act as a subscriber to a given topic. And we built GraphQL extensions for Event Hub and then open source that. So just to talk through a bit more about the pipeline here. We made a lot of contributions to the Apache Behir Twitter streaming connector, where we extended Twitter4j's location features into that connector. We partnered up with a Microsoft accelerator called Tada Web, based in Luxembourg. And what they do is they simulate web crawling. And they're able to extract information from the darknet as well. So their main goal is to try to find that needle in the haystack in the web. We built out Instagram streaming connectors that's able to take images and video from Instagram based on a configurable list of Instagram pages you want to monitor. And then we also open source the one for Bing that I mentioned earlier. And the next big thing is radio streaming. We're able to take any radio broadcast stream, take that, stream it in, and translate that into text, and then treat those texts as another event in the pipeline. And we're able to do this in real time. So we have our Spark streaming cluster here. We have receivers that take these events in. We transform the streaming batches. Then for our feature extractions, we are then extracting various features off these messages. So one is location. We have a spatial database of every place and locality in the world, and we update that through OpenStreetMap. So based on conversation, we're able to, if you mention, say, northern Libya or northern Benghazi, we know the exact shape of that entire political boundary, and we map the event to that area based on the context of the conversation. We extract the topics and the keywords off of that, and then for the computer vision APIs, for any asset that comes in, we then integrate with cognitive services, which is a computer vision set of services offered by Microsoft. And what this is able to do is, based on an image, you're able to detect objects off it. So whether there's an ISIS flag in the image or an AK-47. We built an SDK that they have a speech API that also extends WebSockets. You actually create a streaming audio connection to those WebSockets, and as audio comes in, leveraging their speech API in real time. It's based off of Microsoft's Cortana services. And the text analytics API, which does 15 languages of sentiment. So we also open sourced our own for Arabic, because Arabic is not supported within text analytics. So we have an n-gram corpus of Arabic terms for sentiment. So based on the site definition that's defined in the admin interface, we filter all those events based on the definition. And then the individual messages are then pushed into Cassandra, and then we're aggregating all those events based on a location tile. We have an event hub that our dashboard is then subscribed into. So as results then are pushed to Cassandra, we drop a message on the event hub, and then the revised geotile is then pushed down to the dashboard, and the dashboard re-renders in real time. So the Fortis scenario puts a large emphasis on geospatial context of these events. We disregard any event which we're unable to detect the places and location in the context. So we geotag the mentioned places off the conversations, and as you're zooming in onto the heat map, the newsfeed then is re-rendered automatically based on the map bounds that you've changed. So we're only pulling in the messages that intersect with the bounding box of your map bounds. And then we're also able to filter, the user is also able to filter activities based on the specified topic or the sentiment score. So just to go a bit deeper into how we go about in generating one of these heat maps. In this case, the heat map is generated by summing up the number of location samples in a particular geographic area. So for every location that we detect off these conversations, we attribute that location summary in the heat map. And we sum up over all the locations that are associated with that summary. So just to discuss how we map a particular location point to a geographical summary. So one of the common patterns that we've seen for this XYZ tile concept is also used in OpenStreetMap, in Google Maps, and Bing Maps. So the general idea is to divide the world up into 4 tiles at the top level zoom. And an individual, then for each zoom level below that, then we then take the parent tile and recursively divide it into 4 tiles. And then we do this down to 21 zoom levels. So then an individual tile is then addressed by its zoom level and its row and a column within that given zoom level. So you could think of, if you're in New York City, you mentioned the mayor elections, you mentioned de Blasio, you're mentioning it, say, in West Village and in Main Street. You also mentioned in the tweet South Manhattan in New York. All these layers, they all they all converge with each other. So you need a way to normalize all those different places that intersect. So when you're looking at a heat map, you just care about the general coverage. So the various admin level boundaries are insignificant at that point. So in order to compute our heat map, we use a pretty standard MapReduce algorithm. For every location in the data set, we generate a tile ID key value pair for every zoom level that we want results for. So for this example here, we have a lat long pair, and we're generating the results here are for zoom levels between 10 to 18. And the underscore representation of that is the zoom level and then the row and the column. We then reduce all these mappings with the same key down to its aggregated heat map value. So in Spark, the first element, so in this case, we then are aggregating this up to result into that tile ID with 151, which is the total number of instances of all these location samples. So let's look at what an implementation of this concept looks like in Spark and Scala. We first compute the tile ID for all the zoom levels that we want. So we have those constants above of the min and the max zoom of our tile ID mapper function. It takes in lat long, and it returns a list of tuples, with the key being that tile ID. With this mapper, the overall implementation in Spark is fairly straightforward. We use that tile ID mapper function, reduce it based on summation, and then we take the result, and then we save it to Cassandra. So just to provide context into what the final result ends up looking like in Cassandra. So all the data that we're aggregating up is indexed by the tile X, Y, and Z, as well as a timing period. The data source, whether it's Twitter or Facebook, and the publisher so for Facebook, if we're monitoring, say, Al Jazeera's site or Reuters site, we'd also be able to index it based on that, just so we can aggregate and slice and dice the data based on those various different levels. And then we index it also by topic. So just to provide some details on what some of the messages look like. So as these messages come in, we're using OpenNER to extrapolate the topics and the locations off of these messages. We take those raw messages, and we normalize them and save them into Cassandra. And this is what we use to filter off of our newsfeed. Some of the other metrics that we're extracting from these messages, other than the topic and the place, is also the detected entity. So with OpenNER, they support named entity recognition. So we're able to then draw interrelationships between not only the topic, but also the mentioned organization. The real-time audio streaming, we set up a long-living WebSocket connection through cognitive services based on a list of radio stream broadcasts. As new audio is pushed in through that SDK, we then take that translated text from that audio, and then we feed it into the Fortis pipeline, and then extract all the topics and the keywords off of that. We've contributed a few different Helm charts for Kubernetes, one being the Spark, another high availability chart for Kafka, and another one for Cassandra, and another for Elk, for logging, for the whole Elastic, Logstash, and Kibana stack. All these are available on Catalyst Code/charts. The different streaming connector contributions we made, one for the Instagram computer vision integration, and these are all available on Maven. So the Bing streaming customized search ranking, one for Facebook. And I'd just like to close in saying that Spark Streaming has made a significant impact in our ability to accelerate our ability to be able to use data for good. It's incredible to see the advancements in the Spark ecosystem over the last few years, and being able to draw more awareness to these humanitarian crises around the world. And I'd like to close with that. And the Fortis solution is fully open source. It's available at Catalyst Code/project-Fortis. And I encourage you all to do more open source. Thank you.
All right, we have time for maybe a couple of questions. Please raise your hand. I'll try to reach you with the mic, or you can come down to the mic as well. All right.
Maybe we have a question.
Any questions? Oh, yeah.
Very interesting. I really enjoyed it. Would like to study in detail some of the elements, components, to assume the project is on GitHub, can take a look. If you would mind to just flip back for a second where the connector links, the Maven links were.
The Spark streaming connectors.
Yes.
Yeah,
Because
so, right.
With my projects, one of the keys, get the data, build the connectors. So the first challenge is data collection. Second is prepping the data. And third one is the learning.
Yeah. So for Twitter, we're using Twitter's streaming, the streaming API for Twitter. So the data is coming in real time for that. And we're batching all of our, we have, I think, like a 3-second interval batch as we're processing the stream. So everything batches up, and then we're able to run our transformation off of that batch. For Facebook, it's a bit more challenging because they don't offer any streaming connector. They don't offer any streaming service. So what we have to do is we have to continually poll Facebook every second. And then collect all the events, and then send that along the pipeline. Same thing with Instagram. We have to poll, and then same thing with Bing.
And do you consider taking a look at Snapchat as well? Do they provide any value? You wanna probably not.
I'm sorry,
Snapchat.
Snapshot?
Snapchat for images.
Oh, Snapchat. Yeah, we're looking to try to integrate with Snapchat. I've been able to find an API that's been released yet. Maybe y'all know, but I've been able to find any hooks into Snapchat. But it's something that we did explore.
Thank you. Oh, one more question. Have you looked at news agencies, Bloomberg or CNN, to get connectors?
Yeah. So with the Bing customized search, you can actually filter for just Bloomberg and for CNN, which is exactly what we did for Libya. We were just looking at news results going through Bloomberg and CNN, just because they're trusted sources, as well as local news and blog sites.
All right, we are out of time. So these slides will be published, so all the links to connectors and stuff will be present on the slides. So please join me to give a round of applause to Eric.